So I'm very happy to introduce an academic who is at the other place in Berlin, at the Technische Universität. Dr. Arianna Borrelli is going to talk to us about rays to waves and beyond, light propagation in historical perspective. Thank you very much.
Thank you. Thank you so much. Thanks for the chance to be here. I am glad and honored to contribute to this historical overview on opinions on the nature of light. And I will focus on the period which goes from the early 19th to the early 20th century, with, in the end, a brief look at situation today. And the period I will focus on is one in which really important, one could even say radical changes occurred regarding the opinions on the nature of light. In the beginning, around 1800, there was a debate whether light should be conceptualized in terms of waves or particles. Then the wave opinion established itself, but then by the early 20th century, doubts had again come up because it had become clear that light sometimes behaves like a wave and sometimes like a particle. These developments were quite complex from the scientific and from the historical point of view. Many authors contribute to them, and it's not possible for me to do justice to all of their work. What I did in my presentation is to focus on some episodes which we today regard as important for this story and discuss them a little bit more in detail to give you an idea of the questions being asked and the answers being found, and to give you also an idea of the broader developments. But many more authors contributed to them, so please do not think that only the authors that I mentioned played a role in that. And in this spirit, I decided to start my story with a series of experiments conducted from 1800 onward by the British astronomer, actually William Herschel. These experiments are about what Herschel called the invisible rays of the sun. And what Herschel did in this experiment was to explore the possible connection between sunlight of different colors and heating power. This was a connection which, of course, that there is a connection between light and heat is obvious from everyday experience. It was always known, and it was always a part of the disputes about the nature of light, whether light and heat should be seen as two different things, for example, different particles or different waves, as we already heard. But what Herschel wanted to look more in detail into was the possibility that light of one color heats more or less than light of another color, which of course seemed to indicate a closer connection between light and heat than possibly assumed. And I should say Herschel, as I said, was an astronomer, so he was not primarily making experiments about light. He was using light as a tool of research to investigate the stars and celestial bodies, but he had, in his astronomical research, become aware of this possible connection and decided to explore it more in detail with an experimental setup, which is what you see there. This is an image from somehow later paper by Herschel himself. The experimental setup is quite simple, and we just talked about sunlight and the color spectrum. Here, as you can see, there is a window which is closed except for a slit. Through the slit, sunlight comes in, goes through a prism, is decomposed into its colored spectrum, which is projected on the table, and Herschel very schematically represented it and put also the names of the colors near it. And what Herschel did was to take a number of thermometers. As you see there, these are thermometers mounted onto wedges. And in his original experiment, he positioned the various thermometers with their bulb, the sensitive part, in correspondence to the different colored stripes, waited a bit, and then noticed that indeed the temperature in all thermometers rose, but it rose more in the thermometer that was placed on the red line than, for example, in the one that was posed on the blue line. So the connection between color and heating power was experimentally demonstrated, but what was even more interesting was that in his first experiments, Herschel noticed that if he positioned thermometers, as you see in this picture, above the visible spectrum, so where you would say with your eyes, oh, there is no light there, still the temperature in the thermometers would go up, and it would go even more up than with colored, with visible light. Of course, for us, this is clear, that's infrared light, that's, it's really powerful, it has a great heating power, but for the time, this was a rather surprising result. And Herschel interpreted it quite correctly by thinking that sunlight contains not only the visible colored light, but also some rays which are invisible, at least to us, to the human eye, but still can be detected thanks to their heating power. So invisible light, and here just let me underscore this point. Until then, as has been also said in the previous talks, light was maybe mysterious in its deeper nature, but as a phenomenon, well, it's clear light is something visible, it's bright, it's opposite to darkness, and then now you have invisible light? What is this supposed to mean? These experiments were repeated by other authors and confirmed, because as you can imagine, this was not something that everybody accepted immediately. But it was somehow one component in the switch which led to the establishment of the wave theory of light. Now, I have here to qualify a little bit a statement made by previous talks. Yes, indeed, the wave theory of light became established during the first half of the 19th century, but it was a rather slow development. The young experiments, which have been already described, played an important role in this context, but they were not really accepted by everybody overnight, also because, of course, at the time it took some time for the results of experiments to spread even only through Europe. But yes, indeed, the evidence of interference was an important experimental element supporting the wave theory of light. And in this context, also this invisible light could be understood in terms, as we do today, of light waves, or at least waves similar to those which make out visible light, but waves that have a different wavelength, which we cannot see, but still can perceive because it's associated with heat, with energy. This was, at this time there were already theories of light as a wave, as has already been discussed. However, the final generally accepted theory of light as a wave only emerged after the middle of the 19th century, proposed by James Clerk Maxwell, first in a series of papers in the 1860s, but then in its final form in a treatise published in 1873. And Maxwell's theory was, of course, not only a theory of light, it was a theory of electrical and magnetical phenomena and of how they are connected to each other. For our aims, the important component of this theory was that it assumed the existence of all-pervading electromagnetic field, which mediates electric and magnetic interactions. But in this field, waves could propagate. There was, of course, as already mentioned, the whole question of what is the medium in which this wave propagates, the ether or not the ether. I leave that topic aside. the point here is that Maxwell proposed that there were electromagnetic waves, and of course this led to the hypothesis that light, visible light, and possibly also this invisible light, should be interpreted as one kind of electromagnetic wave. As is often the case in history of science, at least, for us it's obvious that this is the right interpretation, but at the time this was not generally accepted. Especially in general, also the ideas by Maxwell were not accepted for everybody, especially on the continent. In the case of light as a wave, there was the additional difficulty that this electromagnetic field worked well from a theoretical point of view. It allowed to make predictions about phenomena that you could observe, but it was disputed whether or not you should really believe that the electromagnetic field exists out there. This was, of course, also linked to the question of the ether, but not only. And one has to note that the idea of the electromagnetic field was only generally accepted in the 1880s or a bit later, after the experiments by Heinrich Hertz had shown that had delivered empirical evidence for the existence of the electromagnetic field. Hertz, with this apparatus, which I'm not going to discuss now, Hertz showed that one could produce and detect electromagnetic waves, in this case what we today would call microwaves. And not only this, he could also show that you could manipulate electromagnetic waves in the same way in which you can manipulate light. You can reflect them, refract them, concentrate them, and this evidence was was an essential element for the acceptance of the electromagnetic field, of the idea of electromagnetic field and waves in general, and of the identification of visible light as an electromagnetic wave in particular. Of course, later on you would have, with Marconi, radio and more, so the electromagnetic field was even more generally accepted. Now, again, let me just point out something which a posteriori may seem obvious. In the moment in which you start thinking of visible light as an electromagnetic wave, you have this phenomenon of light loses something more of its identity. It's not anymore opposed to darkness, and it's one manifestation of a much broader phenomenon. Electromagnetic waves, electromagnetic radiation, as it was often called at the time, still is called. And from now onward, the study of light will also be part of the study of electromagnetism and electromagnetic radiation. And it is from that direction that the next important development regarding views on the nature of light came. And it came from a discussion which goes still today under the name of the question of black body radiation. Again, this is a rather complex topic which I would like to discuss a little bit more in detail to give you an idea of the historical developments. And to do this, I have to say a couple of sentences about what was the question of black body radiation, what was the question being asked, what answers were being given. First of all, the premises. Yeah, we are at the end of the 19th century. Electromagnetism, Maxwell electromagnetism is well established, and also another branch of physics has become well established, what we call today thermodynamics. The principles of thermodynamics were formulated and generally accepted during the second half of the 19th century. Now, on the basis of electromagnetism and thermodynamics, two opinions became established and are premises on for this debate. First of all, the notion that material bodies are immersed in electromagnetic fields and constantly exchange radiation, exchange waves with the electromagnetic field, so they emit and absorb electromagnetic radiation. I say radiation and waves as synonymous in this context. And of course, this for all wavelengths, not only visible light, but in principle, all kind of electromagnetic radiation. Now, this is quite easy. The second point regards the properties of what is called still today a perfect black body. A perfect black body is an idealization. Physicists like to work with idealization before they then go on to the real world. A perfect black body is a body which, by definition, absorbs all electromagnetic radiation which falls on it. Although the black body absorbs all external radiation, it still emits radiation. It emits radiation, but it emits radiation which it produces all by itself, let's say, thanks to its internal structure, which of course contains electric charges which are moving. And from the principles of thermodynamics, it could be argued, plausibly argued, that such a body, a perfect black body, emits a radiation, electromagnetic radiation over all possible frequencies, and the distribution in frequencies only depends on the temperature of the body. It does not depend on its size, on its form or anything, only from the temperature. Once one accepted these two premises, then one could ask more specifically what was the shape of this spectrum of black body radiation. So what was the intensity of waves, electromagnetic waves of a given wavelength emitted by a black body at a given temperature T? This was the question. There were, of course, two ways of answering this question. You could try to derive from electromagnetism and thermodynamics with some approximation a formula for black body radiation, or you could try to set up an experiment with some system that was at least a good approximation of a perfect black body and then just measure the radiation. Both these roads were followed around 1900, and of course the expectation was that the two roads would converge perfectly. And this was not always the case. This is one of various diagrams, again from a paper published in 1901, where the different points and crosses are the measurements of the intensity for different values of the wavelengths. And the lines, they represent the predictions of different theoretical formulas that had been proposed at the time. Of course, you cannot really have a formula which is perfectly derived from the principles. You always have to make some approximation, some additional assumptions, so you got different formulas. And what happened was that the formulas which were best, if you want, derived from the principle of electromagnetism and thermodynamics, these formulas did not match experiment, or at least matched experiments only for some wavelengths, but from others not. And the formula which matched best the experimental results was the one proposed by Max Planck. I think this is, his name is well known. So the formula by Max Planck fits experimental results. Now you would think, well, fine, you have a formula which works, case closed. Well, not so fast, because there was, at least in the eyes of authors of the time, and especially of Planck himself, a problem with this formula. Planck, other than other authors who had really tried to derive their formulas from the principles of electromagnetism, Planck had arrived at his own formula by let's say, trial and error. This is a historically rather complex topic, but simplified, one can say first it was just trial and error, combining pieces of different formulas proposed by other authors. Then once it was clear that the formula worked, Planck published a series of papers where he tried to show how you could derive that same formula from the principles of electromagnetism and thermodynamics. And he managed it almost with one little problem. He could derive the formula from electromagnetism, but only by assuming that when a body, a black body or any body, exchanges radiation with the electromagnetic field, that this exchange cannot happen in a continuous way, that there is a minimum of energy that can be either emitted or absorbed by a body for a given wavelength. This minimum of energy was called, according to the use at the time, a quantum. Sometimes people spoke of a quantum of light, sometimes of a quantum of energy, but it was a quantum, a very small but finite quantity. And this, of course, was a problem. Waves are continuous, the quanta are discrete. Should this result be interpreted as showing that everybody had been wrong at the time to think that light is a wave? Maybe it's made out of particles, of quanta. Planck and most other physicists were not of this opinion, also because at the same time, as I've said, electromagnetism had become generally accepted. It worked very, very well for radio waves and electromagnetic cables. And so you could not just go back and say that light or electromagnetism communicates through particles, but how to go on? As I said, Planck and most other authors were not ready to take the quanta seriously, but one later prominent author was, and this was Albert Einstein. Einstein was at the time not yet the prominent figure which he would be later on. This 1905 was the year in which he published the first paper which made him known. And in some of these papers were about the light quantum. What he did was to take this light quantum hypothesis seriously, so assume that at least under some conditions, a ray of light was made out of small discrete packets of energy. He was very careful. He did not speak of particles. Yeah, it's very tricky also from a verbal point of view. Anyway, he used this hypothesis that light is somehow made out of light quanta to explain a series of observations like the photoelectric effect, the specific heats of bodies at very low temperature. I don't go into that. The point is that these were predictions that could be confirmed experimentally or even explained experimental results which had until then been rather mysterious. And so this light quantum started being more and more accepted. One has to say that in this case too, it took some time. It really took some time, and actually this hypothesis of the light quantum was sometimes used against Einstein when he was looking for jobs in the 1910s, saying, oh yes, but that is the guy who takes the light quantum seriously. We should be, yes, the relativity theory is great, but... And it's a fact that it was only in the 1920s that the light quantum, the energy quantum, started being generally accepted, and this was largely because through this hypothesis one could explain what is today known as the Compton effect, a phenomenon which can be explained as really the scattering, the collision between an electron and a light quantum considered as a particle. However, as I already said, this in no way was interpreted in the sense that light is made out of particles, because everybody knew that light, electromagnetic radiation behaves like a wave. So what had to be accepted was that light, electromagnetic radiation, displays a dual character. Sometimes it behaves like a wave, sometimes like a particle. This was a big surprise, let's say. It was something that was not really also spoke about very much at this period, but became more and more important because this double dual nature of light in the 1920s became a template for conceiving the deeper nature of all particles. So from there, the so-called wave-particle duality of electrons, protons, and in principle all particles was derived, if not derived, but this was really a template for conceiving of microphysical entities as being neither waves nor particles, but both. This happened in the course of the emergence of quantum mechanics between approximately 1913 and 1927. I certainly cannot go into this detail, but the point is that in this context it became accepted that also electrons, protons, and all microscopic entities which had been thought of as particles display also a wave behavior, in this case too a very important factor in helping the scientific community accept this rather radical view, where was an experimental one, namely the evidence that also electrons, so particle, can be diffracted in an image which we have seen before for light, but this is an image for electrons which display this typical wave phenomenon of diffraction. This is from a paper by not the first one that showed the element, that was by Davidson and Bremer, but had no picture. So to show you a picture, I go to another paper published in 27, and so to make the story short, in the late 1920s, it became generally accepted that microphysical entities have this dual character. Now, you might think that at this point the light quantum stopped being problematic, but this was not really so. The light quantum, which by this time was usually called photon, this was not the case in the beginning, still in the 30s and even in the 40s was regarded as different from other dual entities like electrons or protons. This was because at this time it was clear that photons could be created and destroyed, but it was not clear that this could be the case also for other particles. So the photon was still regarded as something a bit different from other particles, and this only eventually changed with the advent of quantum field theory. And with this, I jump to my last slide, which depicts the situation today, a bit sketchy. What I should say is that around 1948-49, a theory called quantum electrodynamics was formulated, which was a theory that combined Maxwell's electromagnetism with quantum mechanics. And in the context of the interpretation of this, here we are, maybe I should say, going into the metaphysics. This is the quantum electrodynamics, and more in general, quantum field theory is a theory which is mathematical. It works quite well. It allows to predict a lot of phenomena. How exactly you should interpret the different mathematical elements of this theory is a metaphysical question, to some extent still open, but one thing that you can say is that in the context of, say, quantum field theory, quantum electrodynamics, the fundamental structure of microphysics, they are neither particles nor waves, but rather quantum fields, this mathematical object, which are different from classical fields, like the electromagnetic field. You can think of it also as something which you can go and measure. You can't do that to quantum fields. Quantum fields have empirical manifestation also only in the form of protons, electrons, quarks, and photons, of these microphysical identities which display wave-particle dualities and are all interpreted as the quanta of the quantum field. So in the sense, this view of the electron as a light quantum has now been largely extended to all microphysical entities, and all of them can be created or destroyed under the right circumstances. And here you see, probably you know the term standard model of elementary particles. This is at present the generally accepted microphysical theory of microphysical phenomena. And all of these boxes correspond to different elementary particles, and the photon, gamma, is now one of them. And at this stage today, you can really say that light, the photon, is exactly on the same footing as all other microphysical identities. This is, for today, the end of the story, but of course, I put the question mark because being a historian of science, I know perfectly well that usually when you say that's the end of the story, that's not the end of the story. But this is anyway the end of my presentation. Thank you.
Thank you very much. Again, for the brilliant presentation, but also for the brilliant timekeeping. The eagle-eyed observers of the program will have noticed that we have a few minutes more for this particular part of the program than for the other two presentations, which will allow us to, after the initial questions to this paper, to just pick up any remaining questions to the other two presenters. So we will still have enough time to finish for 1:15. So, but let's start with questions relating to this paper. So, open to the audience. There's a question right at the front.
Thank you very much. Could you tell us a little bit more about some of the stuff that you didn't have time to cover in the earlier part, in the part of the 19th century where folks were still investigating what possibly the relationship between light and electrical and magnetic phenomena could be?
So I hope I understood the relationship between light and electromagnetic phenomena.
Yes, could you say a little bit more about, in the early 19th century, how folks came to believe that there was a connection? Of course, this is synthesized in Maxwell's equations, but before that, right?
Well, it's. I mean, I have now to also refer back to the first talk, which also covered that topic quite quickly. Well, first of all, there are two elements. One is a little bit what I said that. Let's say in the first half of the 18th century, there was this transformation where light was not seen anymore as only something visible, but as a manifestation of something wider. The possible connection between light and heat was a topic. And here I must say there was a great variety. If you look around 1800 or the end of the 18th century, there were, for example, in Lavoisier's chemistry, you had light particles and heat particles. And then in other wave theories, you had let's say light waves and heat waves. And there were different versions of all of these views. In the early 19th century, the wave theories of light, especially the one by Fresnel, was developed. And in that theory and other theories connecting to the possible polarization of light provided a mathematical starting point for Maxwell's theory. So Maxwell's theory built upon these theories of light. However, he was mainly focusing on electromagnetic phenomena, on the connection between electric and magnetic phenomena. So it's in this sense, please correct me if I'm wrong, anyway, anyone in the audience, it's an extremely complex story because For Maxwell and his group, let's say later the so-called Maxwellians, there was, from the beginning, a connection between the light and electromagnetic phenomena, because they connected electromagnetic phenomena to the field and to the ether. And the ether was one part of the wave theory of light. However, for other authors who did not connect electromagnetic phenomena to the ether, this whole part, this connection which was there mathematically in Maxwell's theory was, yes, it was a useful mathematical connection, but it should not be interpreted realistically. And that's why the idea that light is an electromagnetic wave was not accepted. I'm not sure this answered your question, because the problem is that one thing is whether a theory existed, another thing is whether it was generally accepted that this theory explained the phenomenon, if you want, at a metaphysical level.
Thank you very much. Over there. Yep. Thank you.
Thank you. Do we understand why the speed of light is so fundamental? Do we understand why the speed of light is so fundamental?
You mean now or historic?
No, not historically. I mean now, currently in general relativity and so on.
Yeah, well, the speed, I mean, that light propagates at a constant speed. This was already part of Maxwell's electromagnetism. And actually, it's from there and on that basis that there's a special theory of relativity was formulated. So this was, this was, I think, mentioned also in the first talk, that light propagates at a finite velocity was established, was generally accepted in the context of, for example, Maxwell's theory of light. This was also expressed in the mathematical theory. So it's fundamental in the sense that it's an empirical result, and it's also a fundamental element of Maxwell's electromagnetism. And from there also of all the later theories based on that.
Yes, but its unchanging value is what governs the relationships between space-time and mass energy. So do we know at a really fundamental level why that is so? Why it doesn't change?
This will actually be picked up in one of the talks this
afternoon,
which will focus specifically on that. So
sorry
maybe
to
we
jump
can.
ahead.
No, it's fine. But I think we can probably leave that until after that particular presentation. Any other questions? I see one in the front. I just need to make sure that I don't miss any at the back because I'm looking into the projector light. Yes, thank you.
Thank you. That's a lovely talk. I was really fascinated that you chose right at the end to generalize the gauge boson nature of the photon to the other gauge bosons of the standard model. And I wonder if I could just push you a little bit more about why you did that. To what extent in your thinking are the W and Z bosons and gluons, for example, a generalized light? Mm-hmm. Is that why you did it? And if so, or maybe not so, are they historically, in your historical survey, are there early suspicions of generalized light that might have other properties, which actually don't travel at the speed? So those are examples, of course, of vector gauge bosons which do not travel at the speed of light because they possess mass.
Yes, thanks for the question. So first, I should say that I decided to add this view of today also because it was important to arrive to today, but it would not have been possible to do the history arriving to that. So this is why I put it. And then looking from today, I think, for me, it is, if you think about the nature of light, it's extremely important, and that's a place of light in today's microphysics, yeah? That's it, it's one particle or one quanta among others, yeah? So I think this is really radical, yeah? Light, in a sense, has lost its visibility, if you want. So this is one point why I showed that. On your question, well, this is a historical question of great importance, and there is no doubt that for the development of the, say, of the standard model, so the W, the Z, and so on, for that, at least from a mathematical point of view, electromagnetism or quantum electrodynamics was the template. So the photon as a gauge boson, it was not yet called as a gauge boson, but that structure was the template to formulate the further theories. So very definitely from a mathematical, theoretical point of view, that was the line followed. Yeah.
Thank you.
Thank you. There's one question here, and anybody else in the back? Yeah, just over here.
Thank you for a very interesting talk. I wonder if you or one of the other speakers could comment on Isaac Newton's ideas about particles and waves for light. Years ago, when I was young, I read his Optics, and I was clearly he was a particle light man, but he was aware of interference phenomena which he had to account for, and he said that the particles, I think, took fits of being easily reflected or easily transmitted. And he calculated the interval between the fits as, if I remember, it was 1/84,000th of an inch. Now, if you put that into new money, it's about 300 nanometers, which is half the wavelength of sort of visible light. So he'd actually calculated the wavelength of light as I see it. But I wonder if any of you or any of the other speakers would like to comment on that, please.
Well, I mean, on this specific calculation, I cannot comment because I don't know enough about that. Maybe other speakers or someone else can say something. On the particle wave notions that are there in Newton's optics, well, that's from a historical point of view an extremely exciting topic, because he has very varied opinions, which also change in the different editions of the optics. And I think there has been quite a lot of discussion among historians which view he actually adhered to. This is, I think, quite typical of Newton, because also in his writings about gravitation, does he really believe that there is a force of gravitation or not? This is a very much discussed topic in the history of science and in the study about Newton. What exactly he means about that it's a mathematical construction and so on. So this is my part of the answer as far as I can go. Maybe.
I don't know, Mark, Olaf, do any of you want to?
I might just comment, not that I have any particular expertise in the details of Newton's core particle theory, but as I tried to emphasize in my talk, we think of light, say light as a particle, or the ether as a material. All of these people were very aware that if they were particles and materials, they are not like regular matter. They are a different sort of substance. So we can't just say that if he's saying like a particle, it's like these particles or something. It's a different sort of substance. And so we've got to be quite careful in what we try to take these things too literally by our sense.
You've got the microphone. If you could just, the gentleman over here. Yeah. Yes.
Thanks. This is just an answer to the previous question. I think that Newton's fits were a dim perception of the quantum amplitudes, Feynman path amplitudes. He dimly perceived that that's what you would, something like that. He didn't have the complex numbers, but he dimly perceived that that's how you could get particles to interfere.
Thank you. One more question over there, and then I would suggest. Sorry?
It's really yet another comment on the same question.
Okay.
So I
So I'm really just commenting on the same question, but I think, again, God, I'm just commenting on the same question again. I think Newton's view was very much the particles are like mini billiard balls, and that's sort of what we describe when we talk about muons. I used to work with muons and these things. And we contrast that with the sort of traditional wave optics view of light as this sort of big sloshing entity in the electromagnetic field. And we've kind of forgotten that actually this theory, which we've got in front of us at the moment with wave-particle duality, is about somewhere in the middle. So they're not. Newton's corpuscles were like billiard balls. Photons aren't billiard balls. They're not really meant to be. They get simplified in these diagrams like that.
Thank you. I think this is now a convenient time to open up the questions to all three speakers. Feel free to stay here rather than disappear back to your seat. If there are any other additional questions or comments on any of the three papers, yes, the gentleman in the middle.
I was actually going to comment. So the second talk, sort of at the start, there was a comment about philosophers don't really see colour as important as things like God or souls. But actually, I mean, I wondered how much that's really true, because in the sense that I'm old enough, as I guess many of us are, to remember black and white television. And I don't think there was any difficulty about watching black and white television or black and white films. So in fact, it seems like from our perception, although colour is a familiar thing in the world, we don't need it. That actually, if you take the colour away and just watch in black and white, it's still perfectly good. So did philosophers, in fact, seriously consider colour, or did they just ignore it, basically?
I'm not sure whether this
was for the second.
A particular.
I can comment on that.
Yes, please do.
Yeah, just television is an adaptation from evolution, because if you're eating a ripe fruit, you want to see it's red, because it's a sign it's ripe. So if you're watching an apple on TV, you don't know if it's ripe or not. Whereas if you're an animal in the wild and you see a red apple, you know you can eat it. So evolution makes us see the information that's essential for survival. That's why you develop things like we heard before. Polarized light doesn't seem to be important for our survival, so we don't see it, whereas color is important. That's why we see it.
That's a different question. I'm saying there are specific things in which color is important, but it seems like most of the time it really isn't, because if you watch it without color.
Yeah, but watching TV, your survival doesn't depend on watching TV. Whereas trying to find ripe food is. Sorry, that's. Yeah, you don't need it to watch a film, that's correct.
Right. So, could you just pass the microphone to that gentleman? Thank you.
Can you make any comment about what people might call slightly abnormal colour perception? There were, I understand. Hang on. I understand in the eye, for example, there were two red receptors that have they're tuned to slightly different frequencies, and this probably amounts to why some people, let's say, some lady with orange hair will wear a red dress that clashes very badly, and for other people it doesn't look bad.
Well, yeah, sorry, you have to see it in the whole context of evolution. You know, there are defects which are obviously of a disadvantage. If you live in human society, even though you might have a disadvantage when you come to a red light, you still, you go to a shop and you buy food, you survive. Whereas if you're an animal in the wild,
I accept all that.
It feels like
it's a defect, but we can live with it because
it feels like we are moving into very organically into the lunchtime conversation. So I think this is now a good time to just remind us of the progression of the program for the rest of the day. So we will have, after putting our hands together, to say thank you very much to our three speakers once again.